Chapter 6.5, Trigonometric form of a complex number. Okay, this is going to be a little bit weird. It feels like it's kind of out of place, but it does have similarities to vectors, so that's why it comes in. When we actually change it to trigonometric form, I'm going to give you guys an equation, and I want you to write that equation on your identities page. Okay, so this is one equation that needs to go on your identities page that you can use for the final. So first thing we're going to do is a little bit of review from Algebra 2. So plotting and finding the absolute value of a complex number. If you remember, a complex number is just a real plus an imaginary part. Okay, so we have a real number being added or subtracted to an imaginary. Okay, and technically any number can be a complex number. 2 is a complex number. It's like we have plus 0i. Negative 4i is a complex number because it's like we have a real number minus an imaginary number. So technically everything is a complex number. We just don't actually call this a complex number. We call it just 2. And this one we usually just call an imaginary number. But we can make everything complex because it's a math and we are good at making things complex. Okay? Or complicated, I guess is more like it. So first thing we're going to do is we're actually going to be plotting these. In mathematics, we like to be able to visualize and represent different things. Good joke. Never trust a math teacher because they're always plotting something. Okay, sorry, not funny. But what we're going to do is, if you remember from Algebra 2, when you plot, oh, it froze. There we go. If you plot a complex number, your x-axis is your real axis, and your y represents the imaginary. So this is really a positive in the 5 in the 5 in the real direction, positive 1, 2, and then positive 6 in the imaginary. Okay, so this would be my complex number, the representation of that on a graph of the complex number 5 plus 6i. Okay, if we were to look at the absolute value, so that's the next part, and I'm just going to erase this real quick. If we look at the absolute value of that, and we think about what is absolute value. Okay, normally you think about, oh no, the absolute value, it just makes everything positive, right? The absolute value of negative 2 is 2. But if we look at the definition, it's the distance from 0. And in this case, on my graph, on my plot, my distance from 0 is the distance from the origin. So we're looking for this distance. Okay, and I mean, as I said, this kind of is similar to vectors. It has some overlap in concepts, but we could think about this a few different ways. We could look at this as we have a distance of 5 and a distance of 6. We could just do the Pythagorean theorem. So we could find the Pythagorean theorem, 5 squared plus 6 squared equals c squared, and that would give us this distance from 0. You could also think about it as this is also considered a magnitude. So the absolute value of a complex number is very similar to the magnitude. So what we can do is the absolute value of 5 plus 6i of that complex number is simply the square root of 5 squared plus 6 squared. So we got 25 plus 36, which is 61. So the absolute value of 5 plus 6i equals the square root of 61. Okay, the absolute value is always going to be a number. It's a distance from 0. It should be positive. So always a real positive number because it's a distance. So we've plotted and we found the absolute value. Okay, let's look at B that I erased. 2 plus 2i. So again, if you graph it, you've got your real, you've got your imaginary. 2 in the real, 2 in the imaginary. There's my plot. And then the absolute value we know again is that distance from 0. So that's just going to be the square root of 2 squared plus 2 squared. Okay, if you notice we don't put the I because we're talking distance. Okay, so that would be the square root of 8, which is 2 square root 2. So the absolute value of 2 plus 2i is 2 square root 2. So my plot and my absolute value. If you were to plot, just real quick, 2 is boring on the real. That would be my plot or my representation of the complex number of 2 because it has 0i, and the absolute value of this is 2. Kind of silly. But if we had negative 4i, that would be our representation, and again the absolute value of negative 4i is the distance of 4 because that's the distance from the origin. So that's our first little bit. As I said, this part right here is kind of similar to vectors because we're the absolute value is like the magnitude of a vector. These aren't vectors, but they have similar characteristics. Okay. Next thing what we're going to do is we're going to represent graphically and then find the trigonometric form of the number. Okay. First, we technically already graphed this one, so I'm going to just graph it real quick. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. So trigonometric form is very similar to the polar vector form. Okay. Sorry, it's bothering me. So in the polar vector form, if you remember, I'm just going to write it over here, polar vector form, we had the magnitude of our vector and then our angle. So if we had a magnitude, let's go to this one right here. If we think about it, the magnitude, or in this case the absolute value, would have been square root 61, and then we would have to find this angle in polar form. If this was a vector, we would then find this theta. Okay, so that's in polar form. In trigonometric, it's somewhat similar, but instead of doing an angle, they want the sine and cosine. They want the trig ratios in there so that they can identify your x and your y. Okay, so what we're going to do is on your identities page, I want you to write this equation. Okay, it's going to be r cosine theta plus I sine theta. Okay, so you're going to write that down. So R represents the absolute value of your complex number. Okay, so that's R. R is going to be our absolute value. It's kind of like our magnitude. And then to find our sine and cosine. So let's look at this. So we have this as square root 61. And we know that this is like x. Sorry, that's a y. And this is x. And theta is right here. Sorry, let me draw this a little bit bigger. Okay, so this is square root 61. We have our x and y, and we actually know what those are. That's 5, That's 6. So we want to find theta. A lot of times we just go with tangent because then we don't need to have this hypotenuse. So if I go tangent of theta equals opposite over adjacent. So theta equals the tangent inverse of 6/5. And okay, go ahead and make sure your calculator is in degrees. And we're going to go tangent inverse of 6/5. And we get theta is 50.2 degrees. Okay, and we're going to end up rounding that one just a bit. So, if you notice, if I look at this, if I wanted to do sine of theta, so sine of theta equals opposite over hypotenuse. If I look at cosine of theta, that is adjacent over hypotenuse. So square root of 61 sine theta equals 6. Square root of 61 cosine theta equals 5. So really, 5 is square root 61 cosine theta. If I put it in my calculator, the square root of 61 cosine, yeah, let's do cosine, of my angle, I'm going to get 5. If I did the square root of 61 of sine of my angle, I'm going to get 6. So really, if we look at this, we've got this right here, and I'm going to erase my example B. I didn't leave myself enough space. And I accidentally. Okay. So if you look at this complex number, this is 5 plus 6i, which is the same thing as square root 61 cosine theta plus I square root 61 sine theta. And we could take out the square root 61. So cosine theta plus I sine theta. And in our case, theta was the 52. So our trigonometric form is going to be square root 61 cosine 50.2 degrees plus I sine 50.2 degrees. And there is my trigonometric form. Okay. So really, we've taken something that looks very simple and we've really made it very complex. But they mean exactly the same thing. It's just the trigonometric form. Yeah, and you could always check that. Again, as I typed in square root 61 cosine of my 50.2, I got the 5. If I typed in square root 61 sine of 50.2, I got cosine. Okay, we're going to just do one more of those. Yeah, let's do one more. This is going to be a longer video, but I think I'll just do one video. So let's say we have -1 minus square root 3i. I want to graph it, and then I want to find the trigonometric form. So if I graph it, 1, 2, 1, 2. Okay. So we got your real, your imaginary, -1, and then square root of 3 is about 1.7, so it'd be about here. So there is my complex number. Okay, so again, in trigonometric form, sorry, I got lazy, didn't want to write it all out. R cosine theta plus I sine theta. First thing we need to do is find the R. The R is that absolute value. So R equals the square root of -1 squared plus negative square root 3 squared. Never put the I in the absolute value. So r equals the square root of 1 plus 3. So r equals 2. So I have 2 cosine something plus I sine something. We got to find that angle. So we are going to find this angle. We know that this is negative square root 3, negative 1. So if I do tangent of theta equals opposite over adjacent. So I'm finding tangent theta of square root 3. So theta equals tangent inverse of square root 3. And we could type that in our calculator in degrees, or we could look at our unit circle. Either way, we're going to come up with the angle of 45. With these, if I'm typing my calculator, I just tend to like to use my my mode to be in degrees. Okay, but we can't just slap in 45 and say we're done, because unlike the last one, which was in quadrant 1, this is in quadrant 3. So what we need to do is we need to actually find this whole angle. So we know that's a plus 180 degrees. So we're going to take 45 plus the 180. So our angle is actually, theta is 225. And we could do a quick check if we wanted to. So 2 cosine of 225. Okay, did I add let's see, hold on. This is not 45. I lied. That is very bad that I lied to you guys. I apparently do that. That should be 60. Okay. 60. I was like, I checked that and I wasn't getting the right answer. So, bloops. So, 2. So, 180 plus 60, on the other hand, is 240. Sorry. Okay, so this is cosine 240 plus I sine of 240. Let's check that. 2 cosine 240, negative 1. Good. Oh, you guys can't see that. I'm just checking it. And then 2 sine of 240, negative 1.7, or negative square root 3. Good. So here is my trigonometric form. Normally we go over a little bit more. We'll go from trigonometric form to standard form, but with the way things are set up right now, guys, we'll just do the from standard to trigonometric form. If you guys are interested in doing it the other way, going back and forth, send me an email. I'd be more than happy to make a video explaining a little bit more. As I said, we kind of cut things out for time-wise. You do need to know how to do this. Hint, hint for the final. So make sure you know how to go from this complex number to its trigonometric form. Okay, guys, have a great day. Bye.